All right, you guys. So I'm just going to work through these day 2 notes. I'm going to move pretty quickly, and I'm going to actually skip a bunch of problems because there's a lot of examples on here that are repetitive, but I will have them completely filled in the completed notes in Canvas. So you can always go look there. Sorry. So today's actually a really important day. I hate that I'm not there to teach it. So we're going to be finding the area of regular polygons today, right? So before we learn how to find missing angle measurements of polygons, right, depending on their total interior degrees and exterior degrees. But now we're going to use some of that knowledge to figure out what the area of the polygon is, okay? So before we actually get to the area formula for a polygon, we need to do some vocabulary, okay? So here we go. So just remember that all regular polygons have congruent sides and congruent angles, which makes them very special, which means they're perfectly symmetric, right? There's a million lines of symmetry going on. All right, so all regular polygons have 3 things. They have apophthegms, right? I've heard some people pronounce it apothem, which sounds very British to me. So I've always called it an apophthegm, but if you want to call it an apothem, you are more than welcome to. A radius, so radii is plural for radius, and then a central angle. Okay, so every polygon has, all regular polygons have these 3 things. If it's not a regular polygon, then it doesn't have apophthegms, radii, or central angles. Okay, all right, so let's learn what all these things are. All right, so an apothem. An apothem is a segment that is drawn from the center of the regular polygon. So on this, there's a hexagon right here. So there's the center. So it's a segment drawn from the center of a regular polygon to the midpoint of any side. So I'm going to drop a segment to the bottom. That's kind of crooked. I don't like that. Right? And that is going to be the apothem. I'm just going to label it with an A. It is a midpoint, so I'm going to put little congruency marks here and here. Sorry. And naturally, if that is the apothem, if I'm splitting the sides in half, then that means the apothem is a piece of the line of symmetry, which means it also is cutting this angle in half. So naturally, whenever you draw an apothem, it is not just a bisector, but it is a perpendicular bisector. Oh, I'll write the whole thing out. I'm being lazy. Perpendicular bisector. That's long words. Okay, so that's an apothem, right? And now how many apophthegms does every hexagon in this case have? Well, I can clearly draw 6 different apophthegms, right? I could draw an apothem to this midpoint, and I could draw an apothem to this midpoint, and draw an apothem to this midpoint, and so on and so forth, right? So however many sides my polygon has, I have that many apophthegms. Okay, now you don't need to sit there and ever draw more than one apothem, right? As you'll see here in just a few minutes. So just find one apothem. I always drop my apothem to the base down here. Now you don't have to do that. You can draw your apothems wherever you want. Okay, so let's move on to radii. All right, so a radius, a lot of people think that only circles have radii, but regular polygons do too. And I hope that's pretty obvious because if I were to draw a circle around a regular polygon, it would fit perfectly, right? That only really happens with regular polygons, right? So I can totally draw a circle around it. And whatever the radius of the circle is, that is also the radius of the pentagon, or the polygon, in this case, hexagon. So a radius is drawn from the center to a vertex. Notice that's also the radius of the circle, right? Because I've gone all the way to the edge, right? So a radius is a segment drawn from the center to a vertex. All right, so this is I'm going to put an R for radius. Now, what else must be true about this radius? Well, if I drew another radius going here, do you see how that's actually a line of symmetry, right? So that means that not only is my radius being drawn to a vertex, but it's also cutting this angle in half, right? So he is naturally an angle bisector, which is good for us because we literally just learned how to figure out what all these angles are yesterday. All right, last one is a central angle. Okay, so a central angle is an angle whose vertex is at the center. Everything happens at the center. Whose sides of the angle are radii of the polygon. So if I identify the center, if I draw two consecutive radii, so that's a radius and that's a radius, right? Then I have created this angle right here, right? And that is a central angle. Okay. Now, how many central angles can I draw? Well, obviously I could draw a radius here and create another central angle. And I can draw another radius here, which creates another central angle. And so on and so on. Another central angle and another central angle and another central angle, right? So you can see if I've got 6 sides, then I'm going to have 6 central angles. And what must be true about all of the central angles that I can draw? Well, they're all congruent. Now, if they're all congruent, can I find the measure of each one of those central angles? Why, yes, I can, because if I go all the way around, I know all of those angles have to add up to 360 degrees, right? Because you've literally just gone a full circle on the interior there. Remember, I'm not talking about these angles. These angles do not add up to 360, right? We learned that yesterday, right? I'm talking about the central angles in the center. Oops, right? So I'm talking about adding all of these up. And no matter what shape I have, those all would have to add up to 360 because you're doing a full complete circle on the inside. Okay, so I know I can just take 360 and divide by 6 in this case, or n, right? And that's going to give me 60 degrees. So I know each one of those central angles is 60 degrees. Okay, I'm going to erase all this extra stuff. All right, so how can you find the measure of the central angle of any polygon? 360 divided by n. And remember, n stands for the number of sides or the number of angles, right? It's all the same number, so it doesn't really matter. All right, now we're going to put it all together. Here we go. This, if you've never seen this formula before, this is the formula, is the area of a polygon formula, right? Area equals 1/2 AP. Notice the lowercase a, right? So it's 1/2. The A stands for the apothem length. So if you're given that, great. If not, you'll have to find it. And P stands for the perimeter. Okay. Now I'm hoping that makes sense because every single regular polygon can literally be broken up into triangles. So we're basically doing 1/2 base times height to find the area of each triangle. And then we're multiplying by how many triangles there are, which is technically the perimeter, right? So that's where this formula comes from. Notice it looks very similar to 1/2 base times height. We're just multiplying by 6, which is where the perimeter comes in, to get the area of all 6 triangles added together. But what if it's not 6 triangles? What if it's 100 triangles or whatever? So I don't really want to have to do all that math when I can just do this formula that works for all regular polygons. So 1/2 AP is the formula that we're going to use. Now, in order to find the apothem and the perimeter, to use the formula, you might have to do a little bit of work. If you're lucky, we'll give you that information, but probably not very often. So the first thing that you need to do is you need to go find the right triangle. And I don't know why, but I always draw my little right triangle in the bottom left corner right here. Always. Again, I don't know why, I just do. So you can draw yours wherever you want. Now, where did this right triangle come from? Well, clearly it has an apothem is the height of my right triangle. And then the radius, the closest radius, is the hypotenuse of that right triangle. And then notice right here, the base of my right triangle, it's not a full side. It's a half of a side. So that's really important, right? That the base of my right triangle is half of a side length. And you'll see why here in just a second. Okay, the other thing that you're going to want to know is this angle here. And again, you'll see why in just a second. I want to know what this angle is inside my right triangle. Well, is that a central angle? No, right? Because the central angle goes from radius to radius. So this whole thing is a central angle. So the angle inside of my right triangle that I've highlighted, it's only half of a central angle. So when I want to find this, I'm going to draw a little line to it. If I want to find this angle right here, it's half of a central angle. Okay, well, how do I find central angles? I do 360 divided by n. We just did that right up here, right? But I don't want the 360 divided by n. I want half of that. Well, 1 times 360 is 360, and 2 times n is 2n. So this becomes 360 divided by 2n degrees. And that would be the measure of that top angle inside of my right triangle. Now, could I figure out what the measure of this angle right here is because it's a hexagon and then divide it by 2? Yes, but that's so much work because every shape is going to have a different angle measurement, whereas the 360 is constant for everybody. So I'm just going to use that top angle. But if you want to find the bottom angle, you totally can. And you're probably asking, like, Miss Chester, why do we even have to find angle measurements? That has nothing to do with the formula. But here we go. It does. So here we go. For each regular polygon below, we're going to draw and label the right triangle because I actually don't even need the polygon. I just need the right triangle so I can find the apothem and perimeter and then use the formula. Okay, so here we go. If it's an equilateral triangle, I'm going to drop the apothem. There's my apothem and my radius. And here's my right triangle right here. I'm going to highlight it. Okay. Now, there's some really special stuff going on if it's an equilateral triangle. First of all, what do we know about equilateral triangles? Well, we know all of their angles are 60 degrees, which means when this little radius right here just split that angle in half, this is a 30-degree angle. Oh my goodness, then that makes this a 30, 60, 90. And that is going to happen in every single equilateral triangle, right? When you draw in your right triangle with your apothem and radius, it's going to create a 30, 60, 90. Okay? All right, let's go to a square. All right. So I'm going to drop my apothem. I'm going to draw in my radius. Here's my right angle. This is where I need to focus all my attention. Now, squares are weird because they're easy shapes to find the area of anyway, but we'll talk about that in a second. Now, what do we know about squares? Well, we know in a square, these are all 90-degree angles in the corner, which means over here, when I split that in half with my radius, then that's going to become a 45-degree angle, which means this guy is a 45-degree angle. So inside of every square is a 45, 45, 90 special right triangle, right? When we draw the apothem and the radius. All right, a regular hexagon. I know we already did this a second ago, but here we go. There's my apothem. Here's my radius. That makes a right triangle. Now, this top angle right here, oopsies, sorry, right, this top angle right here. So there's two ways you can figure out this triangle. You can either find that angle or you can find that angle. I'm always going to find the top angle because I think it's a lot easier. So I'm going to do 360 divided by 2n, n being 6, which is just 360 divided by 12, which gives me, what do you know, 30 degrees. So this angle is 30 degrees, which means this angle must be 60 degrees. So inside of every hexagon is also a 30, 60, 90 triangle. All right, so our little thought bubbles, what do all these regular polygons have in common? They contain special right triangles, which we just took a test on in Unit 5. Now, if you don't remember your special right triangle rules, I'm going to do a quick little recap over here. All right, so remember 30, 60, 90s. You can't forget all the stuff we learned in Unit 5, right? So if this is my 30, this is my 60. That's not a very well-drawn triangle, but you get the gist. So that's x. The hypotenuse is double the short leg, and the long leg is x root 3, right? Then we have our good old 45, 45, 90s. All right. And again, I'm not going to be reteaching this throughout Unit 6, right? We just took a test on this, so I'm going to assume that we're all good with special right triangles, right? So 45, 45, 90, the legs are congruent because it's isosceles, and the hypotenuse is square root of 2 times longer. Okay, so you can't forget all that stuff. We're going to use it again here. All right, now only these three shapes, right? Only equilateral triangles, squares, and regular hexagons contain special right triangles. No other polygons contain special right triangles except for these three, which means if I ask you to find the area of an octagon or a pentagon or a nonagon or anything else, I can't use special right triangle rules. I'm going to have to use trig. Right? So if it's not an equilateral triangle, not a square, and not a regular hexagon, I have to use trigonometry, which again is why Unit 5 is so important. All right. Yay. Now let's get started. All right. You'll notice there's duplicates of all of these first few. I'm not going to do all of them for the video, but I'll complete them for the completed notes if you want to. All right. So example number 1 is a square. Now, I know some of you guys are probably thinking, Miss Chester, I already know how to find the area of a square. You just do side squared. And you're right. That would be 10 times easier here. However, we are not going to find the area of a square using that formula. We are going to use the formula area equals 1/2 apothem times perimeter. Now, on a test or quiz, I don't really care. You can use whatever formula you want for the area of a square. But for today's homework purposes, we are going to practice using apothems and radiuses and central angles and perimeters and all this good stuff, okay? All right, so here we go. You will be given one piece of information and one piece of information only, okay? So they're telling me that the apothem is 10. All right, well, step number 1 always is to draw your right triangle. Draw an apothem, draw his neighboring radius. So I really don't care about the square at all. I only care about this little right triangle inside of the square. And what do we know about this cutie little right triangle? Well, I know he's splitting the 90-degree angle in half, so I know he's a 45, 45, 90. And they told me the apothem is 10, so I'm going to go ahead and label my apothem 10. Okay, well, from here we should be able to label the rest of the triangle, right? Because if that's 10, then this is 10, which means my radius is 10 root 2. All right, well, that allows me to go write in all of this stuff they want me to find. So the radius, 10 root 2 meters. Make sure you put a label on it. The apothem is 10. That was given to me. S stands for side length, by the way, right? Well, I don't really know the side length, but I do know half the side is 10, which of course means the other half is 10, right? Because remember, the apothem is a perpendicular bisector, right? So once we find that leg of 10 underneath, we know that the side length has to be 20. And if each side is 20, and there's 4 of them, then I know my perimeter must be 80. Now, as soon as we know the side length is 20, obviously I can do 20 times 20 to get the area of the square is 400, but not today. Today we're using the area equals 1/2 apothem times perimeter formula. So I'm going to plug in what I know. Well, my apothem is 10, and my perimeter is 80. So half of 10 is 5. 5 times 80 is 400. And not just 400, but 400 square meters. So even though I knew it had an area of 400, right, we just found it a completely new and different way, right? Again, we're not going to be giving you a lot of squares, right? We're just starting nice and easy. All right, example number 2 is basically the same, but they gave you the radius instead of the apothem, so you just have a different piece of starting information. All right, let's go to number 3. This is an equilateral triangle. I don't have to tell you that because we're literally finding the area of regular polygons. So any shape I give you on this paper is going to be a regular polygon. All right, the radius is 8. Okay, well, let's see. I need to drop my apothem. And there's my radius. I'll go ahead and label him 8. And I know my apothem. I'll go ahead and put my little congruency marks there. It helps me out. Well, remember, all the angles of an equilateral triangle are 60, which means this is 30. So there's my 30, 60, 90. All right. Well, this is a pretty easy one to finish labeling, right? Because the hypotenuse is 8, which means the short leg is half of that, which means the long leg is square root of 3 times that. All right, so nice, quick, and easy. Hopefully you remember all your rules. All right, so let's go fill stuff in. So the radius is 8 inches. The apothem is 4 inches. What would be the side length, right? I need this whole thing. So I have 4 root 3 plus another 4 root 3, which gives me 8 root 3. Remember, you're only adding like terms. 4 root 3s plus 4 more root 3s gives me 8 total root 3s. Well, if each side is 8 root 3 and there's 3 of those sides, then I'm going to multiply that by 3, right, which is going to give me 24 root 3. And yay, now that I know all that stuff, I can use my area equals 1/2 apothem times perimeter, because I know the apothem is 4 and the perimeter is 24 root 3. So again, just leave the root 3 alone, right? You're just multiplying the 1/2 times the 4 times the 24. So half of 4 is 2. 2 times 24 is 48 root 3. So that would be my final area. And of course, that's square inches. All right, again, not too bad. All right, let's move on to a hexagon. All right, so hexagon this is telling me it has a side length of 10. Okay, well, I'm going to go ahead and drop my apothem and my radius. I'm going to get this all going here. All right, so the side length is 10. Okay, so be careful. That means this whole thing is 10. Which means this base is 5. Okay, now I also need to remember that the top angle of a hexagon is 30 degrees and this is 60 degrees. And if you don't remember, right, the top angle is 360 divided by 2n. And yes, you need to remember that. Or you would need to calculate each little corner, which again is more work than necessary. So 360 divided by 12 gives me 30 degrees, right, to find that top angle. Well, again, this is a pretty easy triangle to finish off because the 5 is the short leg, right, which means my long leg is 5 root 3 and my hypotenuse is 10. Now, technically, the only reason I'm finding the radius or the hypotenuse is because they asked me right here for it. it has no bearing on the area formula. So if it doesn't ask you to find the radius, then you certainly don't have to. But anyway, in this case, what is everybody? Kilometers. So the radius is 10 kilometers. The apothem is 5 root 3 kilometers. Each side length is 10 kilometers. That was given to me. Well, if each side's 10 and there's 6 sides, then that means that the perimeter is 60 kilometers. And now that I know the apothem and the perimeter, I'm going to put that in my 1/2 apothem perimeter formula. So my apothem is 5 root 3, and my perimeter was 60. And again, I'm going to leave the root 3 alone. I'm only going to multiply the outside numbers. So 1/2 times 5 times 60 is going to give me what? 150 root 3. And that would be square kilometers. All right. Now, so this is basically everything that contains special rights. If it contains a special right, you must use special rights. Do not use trig to do special right triangles, just like Unit 5 tests, right? All right, let's go do some stuff that is not a special right triangle. Okay, here we go. Find the area of a regular pentagon with side length of 8. Okay, here we go. First thing I need to do is draw and label my right triangle down here as much as I possibly can. Okay, there we go. It says side length of 8. All right, so if each side is 8, then that means this is 4. Okay, that's all I know. All right, the other thing I can figure out pretty easily is that top angle right here. Sorry. Right, I need to know what this angle is. Okay, well, remember, it's just a quick, easy formula. It's 360 divided by 2n. So in this case, that's 360 divided by 2 times 5, which is 360 divided by 10, which is 36. So that top angle is 36 degrees. Or if you want to find this whole angle right there and then cut it in half, you totally can. Okay. All right. Well, notice it doesn't ask me to fill in this big long list of information like it did on those first few questions. So it just wants me to find the area. So literally that's all I care about. So I want to know 1/2 apothem times perimeter. Well, the cool thing is I already know the perimeter because they told me that each side is 8 inches long. So I'm going to kind of put a little parenthesis there for my apothem. So the perimeter is going to be 8 times 5, right? So the perimeter is going to be 40. So I can just go ahead and fill that in. So basically all I need is the apothem. Okay, so I'm going to go back to my picture. Here's my apothem. Well, that's the side of a right triangle of which I know at the base and the angle. So now I have to use trigonometry because it's not a special right. So if I use the 36-degree angle, the 4 is the opposite, the A is the adjacent, so I need to use tangent. So the tangent of the 36-degree angle is opposite over adjacent, or 4 over A. So that's going to give me A equals 4 over tan 36. And I know that's gross, but all trig problems are, right? That's why we round to the nearest tenth. So I'm just going to scoochie this over. And I'm going to copy and paste. Obviously, you can rewrite it. I'm going to shove that right in there. That's the apothem. Now, that's obviously going to be a super gross answer, right? If I leave it exact. So it is trig. So anytime you use trig, we are going to just round to the nearest tenth. Please make sure you are in degree mode. And please use your fraction function, right? So I'm literally going to type in, I'm going to go to alpha y equals, I'm going to type in 1/2, or of course you can just type in 0.5, that's totally up to you. And then I'm going to kick out, I'm going to go put another fraction mode in there. So 4 over tan 36. Be sure to close that parenthesis before you kick out, and then times the 40, or 40 over 1, technically. And when I type all that mess in, I get 110.1, which would be square inches. Ta-da. See, it's not too bad, right? I just got to do a little bit of trig work to find the apothem because I don't have any special right triangles to figure it out. All right, let's do another one. Here we go. Number 8. All right, this is an octagon. So I'm going to draw my little right triangle. Notice the more sides you have, the tinier or skinnier the right triangle becomes. So here's my right triangle. I am going to have to find that top angle. So I'm going to do 360 divided by 2n. So it's going to be 360 divided by 2 times 8. So 360 divided by 16, which gives us 22.5 degrees. And again, once you do a lot of these problems, you're going to start memorizing these top angles, right? It's all the same. All right, what else do we know? The apothem length, ooh, nice. They gave us the apothem length is 12. Okay, cool. So I know that the formula is 1/2 apothem times perimeter. Well, they just gave me half of what I need. They told me the apothem is 12. What I don't have is the perimeter. Well, which side of the triangle is going to help me find the perimeter? Well, clearly, I don't care about the radius, right? I want this, right? All right, well, how am I going to find that x length along the side there? Well, this looks like another tangent problem using the 22.5 degrees. So here we go. So I'm going to do tangent of 22.5 degrees equals x over 12, opposite over adjacent, which means x equals 12 tan 22.5. Now, here's where you want to be really careful. You've got to actually understand what's going on here. We're looking for the missing perimeter, right? We're going to fill out something up right here. Well, perimeter is the distance all the way around, right? But all we found was this little piece right here. And what is he? He's half of a side, right? Well, I need the full side length. So what am I going to do? Well, I'm going to double this, which gives me 24 tan 22.5. Again, please remember when you're multiplying trig functions, you're only multiplying the number in the front. You cannot alter the angle, right? That 22.5 can't be changed. Now, by doubling it, this is just one side length. But I still need perimeter. So what do I need to do now? If that's one side length and there's 8 sides, then I need to multiply this by 8. Right, does that make sense? To get the total perimeter. So that's going to give me 192 tan 22.5. Now, could you shortcut this and multiply by 16? Because there's 16 half sides around an octagon? Yes, right? But I didn't want to do that off the bat because I didn't want to lose anybody, right? So I find that. So x was the half side length. I double that to find a full side length. Then I multiply by 8 to find the total perimeter. And that is the lovely number that gets inserted here. 192 tan 22.5. That is the perimeter. Awesome. Now I just have to chunk all that in my calculator and round to the nearest tenth. So 0.5 times 12, which is obviously 6, times 192 tan 22.5. And I'm getting 477.2-ish square centimeters would be my units on there. All right. I'm really hoping this is making sense to everybody. All right, let's go do another one. We're almost done. Find the area of a regular dodecagon. Okay. This one's going to be gross because A, I don't have a picture, and B, they gave me the radius. Man, that really sucks because I don't need the radius. I need the apothem and I need the side length so I can find perimeter, which means I'm going to have to find everything from scratch, right? Using the radius, of course. All right. Now, they didn't give me a picture, but I don't need a picture, right? Remember, I just need the right triangle that exists within the dodecagon. Right? So I'm not going to draw a dodecagon. I'm not going to sit here and spend 30 minutes trying to draw a nice, perfect dodecagon. That's ridiculous. I just need the right triangle. Here's the apothem. Here's the radius. Here's the half side length, right? So I just need to understand the triangle that's existing within the dodecagon, okay? So the radius is 5. So I'm going to label that, okay? I'm going to have to find the apothem and the side length because I don't know either one of them. So if everyone's cool with it, I'm going to label these X and Y. You can use A for apothem, though, if you want to, and whatever for the side length. Anyway, I do need this top angle, right? I need at least one of the angles. The top one is the easiest to find. You can find the other one if you want, but the top one is always going to be 360 divided by 2n regardless of the shape, so that's what makes it easier. So 360 divided by 2 times 12. So that's 360 divided by 24, right? And when we type that in, we get 15 degrees. Obviously, the more sides you have, right, the tinier those central angles become. All right, so here we go. So my formula is 1/2 apothem times perimeter. Now, unfortunately, I don't have either one of those things, so I'm going to have to go find the apothem and the perimeter. So my picture, sorry, the apothem is X, right? All right, so I'm going to use my 15-degree angle on the 5. Let's see, it looks like X is the adjacent, and 5 is the hypotenuse, right? So SOHCAHTOA, adjacent hypotenuse. So this is going to be cosine of 15 equals X over 5. Adjacent over hypotenuse, which means X equals 5 cosine 15. So yay, so I'm going to put in, that's my apothem, 5 cosine 15 degrees. All right. Now I've got to go find the perimeter, which is going to be very similar to what we had to do last time, right? So perimeter means I need to find the Y, which is, remember, a half side, right? Always got to remember that. Well, I'm going to use the 15 again, 15 degrees. Y is now the opposite, and 5 is the hypotenuse. So opposite hypotenuse, that's sine. So sine of 15 equals Y over 5, which means Y equals 5 sine 15. But that's only half of a side length, so I'm going to double that, which gives me 10 sine 15. Right, so that's a side length. But there's 12 of these suckers, so I'm going to multiply this by 12, which gives me 120 sine 15. And that is our perimeter. So that is what I'm going to write up here. So 120 sine 15. All right, then I'm just going to chunk all that in my calculator. All right, here we go. 0.5 times 5 cosine 15. Please make sure you close the parentheses, right? Or else you're going to be taking a sine of a cosine if you don't close your parentheses, so be really careful. And then times 120 sine 15, close parentheses. And I'm getting, what do you know? I'm going to take my little squigglies away because this is exactly 75. when you get to pre-cal, you'll learn about half angles. Since 15 degrees is half of a 30, right? You'll learn about half angles with trigonometry, and you'll kind of understand why that happened like that. Anyway, but it's an exact answer. Yay. All right. I'm doing one more. We're going to do a nonagon. Nonagons are kind of weird because it's an odd number with the 9, but that's okay. So they gave me a picture, which is great. Not that I need the nonagon to be drawn for me, because I really only care about the right triangle inside of the nonagon. All right, I am going to find that, that top angle. So I'm going to do 360 divided by 2n. So in this case, that's 360 divided by 2 times 9. So 360 divided by 18, right, which is going to give us 20 degrees. Right, so this top angle is 20 degrees. That's pretty nice. Now let's see what they gave us. They told us that the perimeter is 54. Well, how nice, right? Because that's something I need for my formula, right? But I also need a label for my triangle. So I'm going to use that to my advantage, right? I'm going to divide by 9 to figure out that each side is 6. And if each side is 6, then that means the base of my right triangle is 3, because it's half of a side. And now I can find my apothem. All right, I'm hoping this is kind of starting to get monotonous at this point, but I'm going to use my 20-degree angle. 3 is the opposite, A is the adjacent, that's tangent, right? So I'm going to use tangent of 20 degrees equals opposite over adjacent. So I get A, my apothem is 3 over tan 20. All right, well, now I can do my formula, right? So area equals 1/2 apothem times perimeter, right? So my apothem is 3 over tan 20. And, of course, our perimeter, they gave it to us. We don't have to do all that multiplication stuff, so we just get 54. And then we can throw that in our calculator and just round that off. So here we go. I'm going to throw that in. 0.5. I'm going to use my fraction mode, so alpha y equals, so I can type in 3 over tan 20. Again, don't forget to close your parentheses. And then times 54. And I'm getting 200, I'm getting 222.5-ish. And that would be square centimeters. Voila. All right, you guys. I hope that was the last one. I hope that makes sense. As long as you can label and find that right triangle, you should be all good. Let me know if you have any questions. I'll fill in the other 3 that I skipped there. They're basically the same. But yeah, hopefully you were able to do your homework with much success. And just let me know if you have any questions. All right, see you guys soon.